Hi everybody, this is Professor Jang of Bugyeong National University, Korea. Today we will talk about frequency domain analysis in image processing. Okay, let's start from filter. We already talked about the filter last time in previous video, so you already know what the filter is, right? So there is something mixed and we want to extract something we need through the filter. Okay, this is the filter. Last time we talked about the spatial filter already, and today we will talk about frequency filter. So, okay, then why do we need filter? Where do we want to use the filter? We want to reduce the amount of the information, and we want to extract more important features from the lots of information. Okay, so if there are too much information, it is difficult to understand, so we want to reduce the information. So this is why we are using the filter. Okay, so but it is up to the purpose. If our purpose is to recognize a person who he is, then we need all the original information probably. But if our purpose is just to recognize whether this object is human or an animal, then we may need only the edge information. That is a lot enough for the purpose. Okay, so then let's talk about the wave. Maybe you feel why you are talking about the wave. There are not much relation between the frequency and wave, but they are very related. Okay, so in wave, so it occurs wave sound. When something moves, that movement creates sound, right? When I touch monitor or something, touch my palm with my finger, then it creates a sound. So when sounds were created, then something we cannot see occurs. That is wave. This wave is transferred. The wave is something moves, right? When I say something, my voice, my throat is moving, and this movement is transferred through the air, and it reaches to the mic, and then it is transferred to the computer, and then it is recorded, right? So this is wave. Wave can be expressed in this way, in 2D. So we see this is almost like a 2D image, but this is not actually 2D image. This is 1D signal, because the signal, when we say this is changing, right? It's changing. There is one point, this point. At this point, something like air, or if there's water, and when I touch this, water does not move. This water bottle is here, but something moves inside, right? Something moves inside slightly. So this is the signal. So so we can draw the movement in 2D, right? So in this graph, the x-axis is the time and y-axis is the amount of the movement, right? It goes up, moves, it becomes strong and weak, while it moves like a right, left, in that way. Okay, so when we are talking about the waves, then we also we can talk how often it moves. So if the signal moves very frequently, we say that this is the high frequency. And if the signal moves very slowly, then we say this is the low frequency. So 1 hertz means that it moves once in a time, once in a second here. So in 1 second, 1 wave. Another 1 second, another 1 wave. If we say 2 hertz, then it moves twice in a second, right? So this is the basic term of the frequency. So I told you that if it moves slowly, then we say this is low frequency, and it moves fast, then it's a high frequency. When you talk or when you sing something, usually guy's voice of the man, often has the low frequency more, and the girl's soprano's voice has a higher frequency in usual. Not everybody, but yes, I mean in general cases. Okay, this happens also the same to when we talk about the sound, like musical notes. When in the musical notes we say that we sing do re mi fa sol la si do, and in that thing the lower note, I can show this is the right English. Lower note, do is the low frequency, and do is the higher frequency. So that's how we are talking about frequency in songs. Okay, and this frequency in signal are also utilized in radio. When you are listening radio signals, there are lots of signals coming into the radio, but we can set the frequency of the frequency of the signal what we want to listen. Then we can filter out all the other signals, and we just listen the only signal what we want to listen. This is how we utilize the frequency in our real life. Okay. Then how we can filter out a specific signal. This is the technique what we call band pass filter. There are four kinds of band pass filters: high pass filter, and band pass filter, low pass, and band stop filter. High pass filter means that it stops low frequency and it passes higher frequency. So we want to listen, or we want to get the higher frequency only. The low pass frequency, low pass filter is used to when we want to get the low frequency signals only. And band pass means band pass filter is used when we want to get a specific band of the frequency signal. And band stop filter is utilized when we want to filter out a specific range of the frequency. That is, if this kind of concept is ideally implemented, then it is perfect. But there is a problem because dividing or distinguishing a specific range of filter exactly is very difficult. So this is these images are the implementation of the low pass filter. The right image here is the implementation of band pass low pass filter with hardware using inductor and capacitor and resistance. It's not that difficult to implement, and we also can implement this filter using software. But when we implement this filter, the response of the filter is a little different to what we expect. You can see the left side image here. And this filter, we want to stop the filter, stop the signal with this frequency in the middle. But here, as you can see, there is a slope, gradual slope. So we want to here we want to make the filter like this. So we want to pass this frequency and we want to stop the higher frequency. But this is it is very difficult to make the filter like this. So this is why we want to, many people tried to build lots of filters. This is the Butterworth filter. This is one of the famous filter. And as you see, the division parts are not very sharp. So some people developed a new filter with a sharp slope. Okay, this is called Chebyshev filter, and this is pretty sharp division area between pass band area and stop band area. But there's another problem here, new problem, is the passed signal here is distorted. So another filter here, Chebyshev type 2, here the passing area is flat, so it looks okay, but here the stop band area is not flat, so we want to stop all the higher frequency, but if we use this type of filter, we also get some higher frequency signals. Okay, so there are some more types of filters, but there are no perfect filter yet. Okay, then what can we do? There are many options in these days, and one of them is Fourier Transform. Every signal can be expressed with the sum of periodic sine or cosine signals. This is what we call the Fourier series. As you see here, there are mixed and pretty complex signals, and this signal can be expressed with the sum of lots of other signals, cosine and sines. And then we can draw these signals, cosine and sine signals, like this. And as you see, some signals has a bigger power and some signals has a smaller power. Right? So here, we can say that a signal can be expressed with frequency, power, and the phase of the signal. I say the phase because here a signal may be shifted, right? So we want to add a sine signal here, but this sine signal can be shifted, right? So this is why we are talking about the phase. The phase means where it starts. Okay, it is shifted. And power means the signal, the size of the amplitude of the signal. So when we divide a signal, a complicated signal, into the many sine or cosine signals, then each sine or cosine signals can be expressed with the power power and phase at frequency. Okay, this image can be expressed in easier way. So the signal is moving here, right? So according to its movement, the power itself, the size of the frequency. So this, the size of the frequency, the power does not change it here. So let's assume that this signal has three types, can be expressed with three types of frequency signal. Okay, this is, we say F0 and F1. This says 00, but we say this is F0 and F1 and F3, F2. Then F0 has the biggest power, right? And then F1 has a smaller, and F2 has a has the smallest power. But as you see, the signal moves. As the signal moves, the phase could be changed. The power does not change, right? Because the signal's power is stopped. But is fixed. But because the signal moves from left to right, so we say when we the phase of the signal is changed. So this can be expressed in 3D space. We often express this in real number and imaginary number. So we can express this with the complex number. Okay, then what happens when we talk about the frequency in images? What is the frequency in image? The signal can be, when we are talking about the signal like waves, it is easy to understand when there are higher frequency and lower frequency. And what is the frequency in image? The frequency in image is the changes of the pixel values in image. So there is if this is the image, black and white, and we can draw its changes, the color value changes, pixel value changes in according to the x-axis. Then we can draw a signal. Okay, this is low and becomes white, and black, gray, black, whiter, black, and white. So we can express it in signal like a wave. See, so in the higher frequency in image means the sudden changes of the pixel values, such as edge or corner. And when you are talking about the low frequency in an image, this is the gradual changes of the pixel values. Okay, then let's check what happens when we apply the Fourier transform to the image. The left image, this is the original image, and when you apply the Fourier transform, it changes into like this. Okay, please ignore the upper part, and when you see the original image here, you see the gradual changes of the color pixels. See, it becomes whiter and darker and brighter, darker and brighter slightly, and darker again. So when you draw a graph using this image according to the x-axis, you can get this kind of graph. Okay, right? Go up, down a lot, and up a little, and go down again. And when you apply Fourier transform this image, you get the image of the right side. And you can also draw a graph according to the x-axis, and the changes of pixel colors will be like this. And this Fourier transform graph denotes the powers according to the frequencies. So here you may notice that the width or length of this graph graphs are the same. Before, the width of the original image was 32, and the transformed image, width of the transformed image is also 32. And here you see the image is symmetry according to the axis, where x is 17. Here, where the point x equals 17 is the frequency 0, so 0 hertz. And when it goes to the right, and as it increases, the higher frequency, higher value in the x-axis denotes the higher frequency. And also, when the value x decreases from 17 to 1, it also means the frequency increases. So this is frequency 0 hertz, and 1, 2, 3, 4, 5, and hertz increases. It is difficult to say that 0 hertz or 1 hertz here, because this signal is not the signal according to the time. This signal exists on the spatial axis. So here, that's why we have the same width of the transformed image and the original image. I changed the labels, x-axis labels, like this, and it was 17, but now it is 0. So I say this is 0 hertz, and it is difficult to say this is 2 hertz, but we just say this is 2 hertz because there are not much better words which I can think now. And this is symmetry according to the x-axis, y-axis here. And what is then the minus 2 hertz? It is the signal rotating the other side of the original of the signal of 2 hertz. So you can just simply think that if the sine signal starting from here to like this, and the minus 2 hertz is repeats to the opposite direction. So it moves the opposite direction like this. So, but if you think a little bit more, then you will notice that the signal itself is exactly the same. So that's why it is symmetry. Then this is image, but this is almost 1D image, right? So it also only has the signals according to the x-axis. Then if there is an image on 2D surface, so this is the image, original image, and if we draw this image into the 3D axis, then you will get this image. So, and this is a 3D signal, isn't it? 3D surface signals. So it is very difficult to analyze it. So to analyze the frequency in this image, we will draw an imaginary axis and we will get the signal according to the axis. For example, let's say this is x-axis and this is y-axis. Then we can draw on virtual axis here. Then we can get the slice. Then we will get the 1D signal. Then it becomes easy, and it's almost same to the previous signal when we try to analyze it. Then we can apply the transforms. And on another axis we can check, and on another axis also we can draw, check and slice, and we get the signal changes. Okay, then finally, if we try to Fourier transform of the original image, and you will get these two different images. One is power and the other is phase. So different to the previous 1D signal, the result of the Fourier transform is 2D images. So two 2D images, right? So the center point here denotes the zero frequency, and when the points are far away from the center point, it becomes the higher. It means the higher frequency. So the most high frequency signal is represented with pixels like this at this corner, or this corner, or this corner, this corner. So here, you will get that previously in the previous slide I explained that to calculate the Fourier transform using 2D image, we need to slice, we need to get the signal according to a virtual axis. So that's why we are doing this. Here, the Fourier transformed information according to the x-axis is represented according to this line. And then when the Fourier transformed information of the according to the y-axis is displayed according to this line. Okay, and then other informations will be denoted according to as the axis rotates here. Okay, and after we get the title of today's presentation is frequency domain analysis. So we can do something with this converted space. We can remove or delete something, or we can add something in this image, and then we can reconvert the frequency image into the original XY spaces. Then we get the modified image. For example, there is corrupted images like this. There is an eagle on the sky, and this image was there are noises of lines, both vertical lines and diagonal lines, and these lines are easily noticeable in the frequency images. For example, this is now here you see it was blacked out, but actually when you see the Fourier transformed image from the original image, this image, then you will see this part is very bright. These parts are very bright, and because of the noise. As you see, this happens because this kind of noises are very. You see, there is a patterns and repeating. The line spaces between the lines here are almost same, so that's why we can the frequency of this noise, these noises are very easy to find in the frequency domain. And then we remove it, just removing the information in the frequency area, frequency axis, frequency space is very easy. We just deleted all the information, so we put the zero, the value of 0 here. Then when we convert it, we say this is an inverse calculation of Fourier transform. Then you will see almost all the noises are removed. There are some noises are left, but it is also difficult to remove all the noise clearly. Okay. All right. Thank you for your listening. Today we talked about filters and why we are using the filters, and what was waves, frequency, and bandpass filter, and frequency in images, and we also talked about frequency-based noise remover. Thank you very much. See you next time.